Psi functions are normalization constant times sine. K values are n pi over a times x, where n is 1, 2, 3, and the energies. Remember, we had defined this symbol as 2 times m e over h bar square. Therefore, energy values are h bar square k square over 2 times m. And allowed values for k are these values. So n square pi square over a square. This is k square times h bar square divided by 2 times m. Let us simplify this. We get h square over 8 m times a square times n square. Now, this is h here. H bar is h divided by 2 pi. There is a pi square here, so after we cancel and simplify, this is our final result. In fact, this constant here, I will give a short symbol, EPS. Now, is it known or unknown? Do we know numerical value of h? Yes. M is given? Yes. A is given? Yes. So everything is known here. What kind of unit should it have? You may understand it by looking at this symbol. What is it? Energy. Therefore, yeah, SI, in SI units, it will be joule. So EPS has a energy unit. So let us write this more simply. EPS times n square. Let us examine the allowed energies. Before doing that, however, because the numerical value of energy depends on which n we select. So we attach the n value as a subscript to the symbol E. Similarly, same thing is true for psi function. Depending on which n we select here, we are going to have a different function. So we write a subscript n to indicate which n we are using. Now we can erase this part. We can show the allowed energies using an energy level diagram. An energy level diagram, there is an energy axis vertically. Let us indicate the 0 of the energy axis. We note that epsilon is a positive number. N square is also positive. Therefore, these all energies are positive numbers. First, ask yourself, does it make sense? Remember, in this problem, think classically. What is the total energy? Kinetic plus potential energy. But potential energy is 0, so it is only kinetic energy. Therefore, what do you expect for the numerical values of kinetic energy? All positive numbers, right? And as you see here, all these, no matter which n you select, there are only positive values. So this is expected. Let us start with the lowest possible value. Lowest energy will be obtained for which selection of n? 1. The result is 1 times epsilon. Epsilon is a non-zero number. So there is I mark on the vertical axis the numerical value of the energy, and next to it I draw a dash. This dash indicates the state. So here we have psi 1. Or let us write E1, and there is a corresponding psi 1. The next value for energy is when we put n equals 2. 2 times 2 is 4. So the numerical value is 4 times eps. It's somewhere here. There is a state. This is E2, and the corresponding function is psi 2. The next value is when you put n equals 3 here. So 9 eps, and this is E3, and the corresponding function is psi 3. So can we continue using this information? Yes, and I indicate it by 3 dots. There is no upper limit. All right. Now let us examine the allowed energy. These are the allowed energies. First of all, do we have an allowed energy at 0? Is there an energy level here? No. Compare it with this, classical. Classically, it is possible to have 0 kinetic energy, but according to these results, we did not find 0 as a possible energy. In other words, 0 is forbidden. It is not allowed. The allowed energies are only these numbers: epsilon, 4 epsilon, 9 epsilon. You see, are they continuous? Are they continuously changing from one value to another one? No, jumping from f's to 4 times f's to 9 times f's. Discrete or quantized energy levels. What is the ground energy level, lowest energy level? Eps. Okay. Now, there is a useful concept called zero-point energy. Zero-point energy. By definition, zero-point energy is lowest quantum mechanical energy minus lowest classically expected energy. This is a general definition. Let us now apply it to this problem. The lowest quantum mechanical energy is E1, and it is equal to eps. Lowest classically expected value is when p squared is 0, then E classical energy will be 0. So there is a non-zero value for the zero-point energy. We are going to use this concept, this term, zero-point energy, for other types of motions also. For example, there are vibrational motions. We are going to discuss vibration of a diatomic molecule. There also we will see zero-point energy from the same definition. Molecules also have rotational motions. We will use same definition. In fact, we will find that for rotational motions, zero-point energy is zero, which means the classical lowest value is the same as quantum lowest level, no difference. When zero-point energy is zero, we say there is no zero-point energy. In words, it means numerically zero. The difference is zero. For the vibrational zero-point energy, we are going to find out that the result is non-zero. So there is a vibrational zero-point energy. Now, to distinguish between different types of zero-point energies, we use additional terms depending on the type of motion. Now, let us examine how can we describe this type of motion. Motion is along a straight line. Such a motion is called translational motion. So, translational motion is along a straight line. Rotational motion is this way, rotating in space. Vibrational motion is like that. We use such terms, vibrational, rotational, and translational. So in this case, we will say more accurate expression for this zero-point energy will be the translational zero-point energy, so that it is understood what kind of motion we are talking about. All right. Then let us examine the distribution of the allowed energies here. We see that the difference between this level and that level is how much? 4 minus 1, 3 epsilon. Difference between that level and that level, 5 epsilon. Is the spacing same or changing as you go up? Increasing. That's one thing we know. That the level spacing between one level and the next is not constant. It is changing. In fact, it is increasing. Okay, now let us turn to the state function, wave function, and determine the value of this A. What was the meaning of A? Normalization constant. Therefore, we are going to use the normalization condition to fix numerical value of A. Normalization condition is psi. Here we have just one variable, so let us write it explicitly. dx. X is all space. What is it? From minus infinity to plus infinity. Our function is this one, but this function is valid only for x values between 0 and a. Because outside of the box, psi function is 0. You see, if you have an integral of this type, you may split. This is a property of integrals, isn't it? Now, for our problem, For x between minus infinity to 0, the function, our function psi, has which value? 0 value. Therefore, there is no contribution to the first integral here. This one gives 0 because f is 0 for all such x values. Same thing is true for this f, because x is after a up to infinity, and the function is 0 everywhere there. Therefore, the only non-zero part is which part? This is 0. This is 0 because f is 0. This is non-zero. In other words, effectively, for this particle, all space is only for x from 0 to a. So this normalization condition, the limits here, formally it is from minus infinity to plus infinity, but because of these properties, it is from 0 to a, and our function, this part is real function. You don't see any complex number I here. Normalization constant can always be taken as a real number. Therefore, we may assume everything is real here, including a. Then, this is our normalization condition because of these facts. Now we put this is a sine square. Sine square n pi over a times x dx. This must be equal to 1. The value of this integral call this I. You may use properties of trigonometric function, sine function, to get rid of this square here and then do the integral. The result is a over 2 after you put the limits. And notice that the result does not depend on n. For all n values, we have the same integral, same result. What is it? A over 2. Therefore, value of the normalization constant is square root of 2 over a. Now that everything is specified, these functions with this a, square root of 2 over a, are normalized functions. Let us see if you remember the concept of orthogonality. If I take this function, psi 1, what is psi 1? Put n equals 1 here. Multiply it with psi 2. What is psi 2? Same expression, but n is equal to 2. Then integrate this. Psi 1 times psi 2. Integrate from 0 to a. What result do you expect? Of course, you may do this integration by explicitly substituting sine pi over a x and then times sine 2 pi over a x and then do the integration, put the limits. But what was our general quantum mechanical principle? If you have two functions, and they are eigenfunctions of the same operator. Remember, all these functions are eigenfunctions. And the eigenvalues are f's, where h is p squared over 2m. Any two functions from a set of eigenfunctions of a given operator are orthogonal. They satisfy orthogonality property. Therefore, whenever you have such an integral, you know the result is 0. Orthogonality. You may take any two functions here. Take psi 2 and psi 8. It will also satisfy this orthogonality property. Knowing the orthogonality property is very useful because we have many problems in which it is just a matter of logical thinking, using such ideas, normalization and orthogonality. And then everything is symbolic. And you arrive at a useful result. Now, what was the definition of EPS here? Let us write it again. H square over 8 times m times a square. Now, if a is a large number, macroscopic number, like 1 centimeter, and the mass here is the mass of a tiny particle, such as a molecule. Because A is macroscopic here, the numerical value of epsilon would be very, very, very small. Or maybe more concrete example. Let me take one water molecule. As the particle. And let us assume the box size A is 2 nanometers. All right? Notice that just one water molecule, and also box size is very, very small, 2 nanometers. It's a microscopic box size. Let us calculate this value. Mass of water is, oxygen is 16 plus 2, 18 gram per mole. Remember the units. Now change it into kilogram. You get 2.989 times 10 to the minus 26 plus minus 26 cannot be plus kilogram. How did I obtain this? Change from gram to kilogram, which means just divide by 1,000. And then per mole, mole means Avogadro's number, 6.02 times 10 to the 23. Then use your calculator, you will obtain this. Okay? Now, with this data, numerical value for EPS from this expression, 4.59 times 10 to the minus 25 joule. To make it more familiar, let us express this number as joule per mole. How do I do it? Multiply it with Avogadro's number. This is 0.276 joule per mole. You see that with this unit, joule per mole unit, this is not a very small number. It's a significant number, isn't it? Now, looking at that, 2 nanometer means 2 times 10 to the minus 9 meters, isn't it? If instead of a nanometer, if this were centimeter, what would happen? Centimeter is 10 to the minus 2 meters. Nanometer is 10 to the minus 9. The factor is 10 to the minus 7. There is a square over there. When you take this square, a square, the factor will be 10 to the minus 14. But you are dividing. Therefore, that number f's, if you take a macroscopic, say 2 centimeters box size, that number would have been 10 to the 14 times smaller than this f's. In other words, as a box size gets larger and larger, numerical value of epsilon is getting nearer to 0. But if f's were 0, remember here, this number would be nearby the other one, and all the numbers are going to be nearby each other. In other words, if the box size is macroscopic, then the allowed energies become similar to, I have erased here, classical values. The same remark is true if the mass is macroscopic. Here, my example was for a microscopic water molecule. But instead of water, if I use this chalk, the mass would be tremendously larger relative to mass of water molecule. That would make epsilon value near 0. So in both cases, when things become macroscopic, quantum effects disappear. Only for microscopic particles and microscopic distances, quantum effects are relevant and they are measurable. All right, let us keep that. Erase this part. Write here f times n square. Let's have an example about probability of finding the particle inside this box. Now, in the exercise 1, calculate the probability of finding the particle between 0.3a. So divide this into 3 sections. Say this is 0.3a and 0.6a. For the ground state. Now, which one is the ground state function here? If you put n equals 1, that's the ground state. What is our expression for probability? This gives us probability of finding the particle inside a tiny interval. The tiny interval is dx. Very tiny, very small dx. But the interval I have given there is not very tiny. It ranges from 0.3a to up to 0.6a. Therefore, to find the probability, we have to add up the tiny probabilities. That means integration. And here, from 0.3a to 0.6a. This will give us the probability of finding the particle anywhere between 0.3 and 0.6 A. The numerical value will be different depending on which psi you put here. How many different psi's do we have? Infinitely many, right? For each n here. For each n, we have a different psi function. Now, therefore, we have to indicate for which state do we want to calculate. Let us start with the ground state. For the ground state, what is the state function? It is psi 1, isn't it? In other words, when you put n equals 1 here. So, psi 1 square, 0.3a to 0.6a. You substitute explicitly. The function must be normalized, and the normalization constant is that one, times sine pi over a x square. Integration limits is from 0.3a to 0.6a dx. When you do the integration and put the limits, then multiply with 2 over a, the result is 0.545. So what does this tell us? Probability of finding this particle in the ground state, it is moving in the ground state, between 0.3a and 0.6a is 0.545, or using percentage format. Remember, a probability is a number between 0 and 1. If you multiply such a number with 100, you express the same thing using the percentage format. In fact, have you used the Excel program? Type 0.545 to one of the cells. Then choose from the menu, choose the style. It says scientific, normal, and there you will also see percent symbol. Select the percent. Don't do anything, don't multiply yourself. Just select percent. Then press the enter. The number will change automatically. What will it become? 54.5, because of the percent. It's not different from bold format or italic format. It's a percent format. So the number is any number. It is simply multiplied with 100, and the result is printed. So it is 54.5%. In other words, I can write equal sign here. Equal. But I have to add this symbol. 54.5%. Together with the percent symbol, it means 0.545. Now, if we repeat this calculation for other states, and we have the results in the exercise. For example, in the first excited state. What is the first excited state here? Which n? N equals 2. The state function is psi 2. You put n equals 2 here. The rest is same. You replace, instead of psi 1 square, you will use psi 2 square. Probability, now you will obtain a different number. It is uh, 17.8% for the same interval. This way, you may calculate similar problems for different regions here. What is the probability of finding the particle anywhere between 0 and A? Between the left wall and the right wall? 1. And how is it done mathematically? Instead of the lower limit, you put 0. For the upper limit, you put A, but then it becomes normalization integral. And we know the result is 1. Let us have some graphical views for the state functions. I will do it this way. I will use this line also as an energy line, the left wall. Then I will indicate my first allowed level, the ground level, n equals 1 here. Then I'm going to draw a axis parallel to the actual axis. Using this axis, I'm going to draw the graph for psi 1. What is psi 1? Normalization constant, which is square root of 2 over a, times sine pi over a x as a function of x. Of course, exactly on the walls, we know that all these functions are 0. So here it is 0, here also 0. And you may put x equals 0, you will have 0. Put x equals a, again, sine pi is 0. The graph is half of a sine wave. It is like this. This is the ground, for the ground state psi 1 function. Now, sometimes using such graphs, we can evaluate this type of probabilities. For example, if you know the graph of psi 1, you can easily draw graph of square of psi 1. For example, this function, does it become anywhere 0 between the left wall and the right wall? No. So when you take the square of it, that function will also have no 0 between the left wall and the right wall. But the square is this. And the integration is area under the integrals, under the curve. So sometimes such graphical ideas help you obtaining numerical values of such integrals. Just draw them graphically and then first draw the psi function, then square of it, and then indicate the limits of integration, and then look at the area under the curve, and sometimes you may easily deduce. For example, from this graph, suppose the problem is, what is the probability of finding the particle in this ground state between 0 and 0.5 a? 0.5 a is exactly middle of it, isn't it? But now imagine doing the integration. Integration is just square of this function, and then the area under, when you take the square of it, it will look similar to this function, isn't it? Then the value of that integral, but the limit is from 0 to 0.5. Would be just this area. You notice that the area on the right side of the middle point is also same as area of the on the left side. The total area under the curve, we know how much is it? The integration from 0 to a, 1. Therefore, the area here should be 1 over 2, which means 0.5. Hence, in this state, in the ground state, probability of finding the particle between 0 and 0.5, the midpoint of the box. On the left side is 50%. What about on the right side? It is also 50%. You see, in this example, I didn't actually do mathematical integration. What did I do? I just drew the graph and then imagined what would be the square of it. And then, just from the graph, I deduced some facts. Sometimes such ideas are very useful. All right, let us repeat this for the first excited state. Again, this time energy is 4Fs. I'm drawing a x-axis parallel, as I did here, to the original x-axis. Now, my function is psi 2, which is normalization constant times sine 2 pi over a x. N is 2 here. Now, the functions are, of course, 0. All functions are 0 at the walls. But this function is 0 at one more point. At which point? When x is a over 2. A over 2 is midpoint. So the function is also 0 here. Now, then you may draw it. This is all right. Okay. This point, which is the midpoint of this point and that point, is what is the value? A over 4. Suppose we have a problem like this. What is the probability of finding the particle between a over 4 and a over 2 in this state? If we use mathematical procedure, what are we going to do? We are going to take this expression. We will write psi 2 here. Lower limit will be 0, a over 4 is 0.25, 1 over 4. 0.25a, and the upper limit would be a over 2, which is 0.5. And then we would do this integration. Okay? But graphically, we can do this easier. Now, it is this region we are talking about. Between. Now, imagine taking the square of it. When you take the square of it, this part will look similar to it. But the negative side, because we are squaring it, it will become positive, isn't it? So, after taking the square, it will look something like this. Right? Now, this is a over 2. This is a over 4. It is this area we are interested in. But from the graph, we see that this area is the same as that area, same as this area and that area. The total of it, we know how much? 1. How many such pieces are present? Equal pieces, 1, 2, 3, 4. Therefore, our answer will be 1 over 4, 0.25, which means 25%. If we actually did that calculation, we would find the same result. All right? Therefore, the point here is that sometimes using graphics could make it easier for you to arrive at some results. But of course, for special values of the limits, here I have taken a over 4, a over 2. But if it were a over 10, right, then you wouldn't be able to use such ideas. It would be necessary to do the integration over there. Okay, we stop here.